Right, back with some quick math. We are still busy with Euclidean geometry. Like the video, subscribe to the channel, share it with anyone that does pure math, technical math. I'm sure they will learn from it, help the channel grow. Right, we've been in Euclidean geometry. We're in theorem 5. This is an important one. This is one that you do need to know the proof of if you're doing pure math. Technical math, you don't need the proof. Pure math, you do need this proof. Okay, so pay attention. This is something you need to reproduce. Right, I'm gonna start by telling you the conclusion. Right, so when we are done, we are gonna say, let's label these, make it A, B, C, and D. A, B, C, and D. We are going to determine that angle D and angle B are supplementary angles, right? The ones that are opposite each other, when you add them together, you end up with 180. Supplementary angles means you add two things together, or you add a number of things together, you end up with 180 degrees. So B and D, when you add them together, you get 180. That's what the theorem is, right? We'll do the proof now. So let's start by certain concepts, right? ABCD is a quadrilateral, a shape with four sides, okay? ABCD. However, this quadrilateral that you are dealing with here is a cyclic quad, right? What that means is, it means our quadrilateral now also falls on the circumference of a circle. So all 4 points that you have over there, A, B, C, and D, all 4 of those points are on the circumference of the circle. So this is a cyclic quad, right? Great. So we are dealing with a cyclic quad. And in order to do the proof, we are going to need the center of the circle. So let's throw a dot there and let's call that center O, okay? The next thing that I'm going to do is, let's put this in another color. We're doing a construction. We're putting in something that's not there. So we are drawing AO in here, and we're drawing OC in. So we've constructed those. And now that we have constructed those, we have two O's. We have O1, and say that's O1. Let's say this is O2. So O1 is on this side, and O2 is on that side. Okay, great. Now, theorem 2, we remember theorem 2, that's an important one. That one helps us again, because when we look at this over here, that is theorem 2, okay? Let's maybe put this in some other color. Let's make it green. And theorem 2 tells us angle at center, so that's going to be O2, is double angle B, right? Let's write that statement down. So we're going to say angle O2 is equal to 2 angle B's, right? The reason for this is angle at center is, center is twice 2 times angle at circumference. Okay, angle at center twice the angle at the circumference. Great. Right. Then we are going to, let's highlight this in maybe orange. Then we are going to look at the shape on this side over here. Again, theorem 2, right? And theorem 2, let's maybe put this in blue. Theorem 2 tells us angle at center. So now it's O1 that we're looking at is double angle D. Okay, so now the next statement we're going to say is O1 is equal to 2 angle D. Reason is going to be the same thing, angle at center is twice the angle at the circumference. Right, so we've made those two statements. The next thing to notice is that when we do look at, put this in orange, when you do look at this O1 and O2, when you look at those together, they form a revolution, right? So we know that O1 plus O2 is a revolution. So O1 plus O2 has to equal to 360 degrees. Why? That's a revolution. So revolutions are a reason, or you can say angles around a point, right? O1 and O2, they equal 360 degrees. What is O1? So we've made these two statements. So we can say O1 is 2 D. And then we can also say O2 is 2B, and we know that they equal to 360 degrees, right? Okay, so let's just take a second to talk about what we said now. We said O1 plus O2. When you look at the picture, O1 and O2 make a full revolution, so they have to be 360 degrees, right? However, we know that O1 is 2D2, so we fold that in there. We know O2 is 2B2, we fold that in there. Great. Now we're going to say there's a common factor of 2. So let's divide everything by 2. Divide 2, divide 2, divide 2. And now we'll see that angle D plus angle B have to equal 180 degrees, right? And that is our theorem 5. So angle D and angle B, when we looked at our picture initially, angle D, angle B, we said that those were the opposite angles of your cyclic quadrilateral. And what we've learned, what we've discovered, is that the opposite angles of your cyclic quadrilateral are supplementary, right? Let's see if we can erase some of these things over here. Okay. Let's get rid of all of those again. So we said angle B and angle D, when you add them together, you end up with 180. Similarly, angle A, angle C, when you add those together, you end up with 180. Right? The reason that you write down when you use this theorem is you will say opposite angles of your cyclic quad. Right, now the handwriting is a bit bad. Let's try that again. Opposite angles of your cyclic quad. That is the reason that you write down when you use this theorem. Right, that's theorem 5.